Alright, now we're going to start chapter 5, section 3. Before starting the section 3, we should first study the title about the magnetic field of the Earth. This title is removed from the original book. It's just in the original book, but in the edition in our hand, this title is removed, but it is very important for answering the questions related to the magnetic field of the Earth. So, before explaining the Earth, we should understand that if you take a magnet has N pole and S pole. So, and magnetic field lines are from N to S. We draw it outside from S to N within the magnet. But if you hold a compass close to this magnet, compass needle will align itself so that N pole of the compass needle will point the S pole of the external magnet. So this is the external magnet. Compass needle is also a kind of magnet, it's tiny magnet. N pole of this tiny magnet will point the S pole of the external magnet. So N pole of tiny magnet will show the point the S pole of another tiny magnet. So then we can say that the unlike poles faces each other for a magnet. Right here N and S is facing, again N and S is facing, right there S and N is facing. So when you hold a compass needle, then you can say that compass needle will align itself in the direction of the external magnet from S to N. However, the N pole of the compass will point the S. So now let's come to the Earth's magnetic field. This is we are using the compass needle for finding a direction. When we hold the compass, we will see that the N pole of the compass will point the geographic North Pole. So this is the geographic North Pole, which is the region of Siberia. This is the geographic South Pole, which is the Antarctica. However, if compass needle is aligned itself like this, if this is the N pole of the compass, that must be the south pole of the Earth. So Earth is behaving like a magnet too. For that reason, Earth's magnetic field will be like this. So Earth's magnetic field will be from the south pole, geographic south, to the geographic north. So this is the normally for an external magnet it was not like this. It was from the magnetic north to magnetic south. But for Earth we say that it is from geographic south to geographic north. This is important when we are answering the questions. If a question is talking about the Earth's magnetic field, so we are going to say that Earth's magnetic field is from its south pole, geographic south pole, to geographic north pole. So according to this information, we are going to answer the questions. Now let's start the chapter section 3. Section 3 is about the magnetic force. Before starting the explaining magnetic force, I'm going to give some brief information about the electric field, which is the title of the 11th class. So there are two parallel conducting plates. One plate is charged positively, the other plate is charged negatively. So if the plate is charged like this, from positive plate to negative plate, electric field is formed. These are electric field lines from positive to negative. When we put a charged particle, for example an electron, between these parallel plates, this electron will start moving. Yani electric field will set this electron into motion by applying an electrostatic force or electric force. However, we don't see the same thing for magnetic field. If we locate the electron inside a magnetic field at rest, this electron will stay at rest Yeah, the net force, the magnetic force acting on the electron will be equal to zero. Yeah, and if you put an electron inside a magnetic field at rest, this electron or proton, whatever, a charged particle will stay at rest infinitely. Then what is the difference between the magnetic field and electric field? Electric field can set a charge into motion, but magnetic field cannot set a charge into motion. So what if a moving charge enters inside a magnetic field? Now, right here, the charge is at rest. For that, is magnetic force is zero. But if charge enters into the magnetic field with a velocity, right as you see here. Now here, an electron is entering inside a magnetic field with a velocity. In this case, there will be a magnetic force acting on the charge. And the charge must move inside the magnetic field to be their magnetic force acting on the charge. So electric charge moving through a magnetic field do experience a magnetic force, and this force has its maximum value when the charge moves perpendicular to the magnetic field. Now, this is important information. If charge moves perpendicularly to the magnetic field lines, right here the magnetic field lines is into the blackboard, into this page. So then charge is coming parallel to the plane of the page. So then these two vectors are perpendicular to each other. So that's why right here the force acting on the charged particle will be maximum. But if charge moves parallel to the magnetic field lines, in this case still there will be no magnetic force acting on the charge, and there will be no magnetic force acting on the charge. Then we can generalize, we can say that magnetic force can act on a charge only if the charged particle crosses the magnetic field lines like this. So charged particle must move. So while moving, it must cross the magnetic field lines. Then we can say that there is a magnetic force acting on the charge. The strength of the magnetic force acting on the charged particle, which is moving perpendicular to the field, is equal to the product of magnitude of the charge Q, magnitude of the velocity V, and strength of the external magnetic field B. So if we multiply these three quantities, we will get the force acting on the charge. B, external magnetic field, Q, charge of the charged particle, V is the speed of the particle. So when we multiply these three quantities, we will get the force acting on the charged particle. But in some cases, charged particle can enter inside the magnetic field not perpendicular. If it enters like this, so because these two vectors are perpendicular, you can use directly this equation. But if charged particle enters inside a magnetic field with an angle theta between the velocity vector and the magnetic field vector, if this is theta, in this case simply you are going to multiply this equation by sine theta. Don't forget, theta is the angle between the velocity vector in direction of the motion and magnetic field vector in direction of the magnetic field lines. So now we will define the unit of magnetic field. Unit of magnetic field is Tesla. Force is Newton. Speed is meter per second. Charge is Coulomb. So now definition of the Tesla is giving you a book like this. If a 1 Coulomb charge moving at 1 meter per second perpendicular to a magnetic field experience a magnetic force 1 Newton, then we say that that magnetic field is 1 Tesla. This is the definition of Tesla. So we can use the equation for calculating magnetic force. Magnetic force is equal to Q times V times P. So we will find the unit of magnetic field. So we should divide the equation by Q times V and Q times V, both sides of the equation. This will simplify. You will get P as force divided by Q times V. So to get the unit of any physical quantity, you should use this equivalent equation. For example, what is unit of the force? It is Newton. What is unit of the charge? It is Coulomb. What is unit of speed? Meter per second. So this is equivalent unit of Tesla. 1 Tesla is equal to Newton divided by Coulomb times meter per second. But we can write this unit in different form. For example, one of them is this one. How can we convert this to Newton divided by ampere times meter? Because we know that electric current is equal to charge divided by time. Electric current unit is ampere. And ampere, 1 ampere is equal to 1 coulomb per second. Now look at here, here's the coulomb per second. Instead of coulomb per second, what can I write? Ampere. So then 1 Tesla can be equal to Newton divided by ampere times meter. Another equivalent of Tesla S can be calculated from the definition of the electric field between two parallel plates. If two plates are separated by a distance of d and applied a potential difference of V, in this case electric field becomes 1 volt per meter. So also electric field can be defined as Newton per coulomb. Then 1 Newton per coulomb is written as 1 volt per meter. This is from the 11th class title, electric field title. Now look at this equation. When you look at it, you see that here is Newton divided by Coulomb. Newton divided by Coulomb. Instead of Newton divided by Coulomb, what can I write? Volt per meter. Now I am going to write instead of Newton per Coulomb, volt per meter. Then turn this second to upside down. So then volt times second divided by meter times meter square. This is another equivalent of Tesla. So then Tesla is equal to Newton divided by Coulomb times meter per second. 1 Tesla is equal to Newton divided by ampere times meter. Or 1 Tesla is equal to volt times second divided by meter square. All these three are the equivalent of 1 Tesla. So most magnetic fields are much stronger than 1 Tesla. Around you in daily life, you don't experience huge magnetic field. For instance, Earth's magnetic field near its surface, where you live, is about 50 microtesla. It's, as you see, very small. 550 times 10 to the power of minus 6 Tesla. As you see, it's very small. But if you want to generate a magnetic field which is strong, you need to use the superconducting materials. We are going to study superconductors in the 9th chapter. So the superconducting magnets can generate as great as 30 Tesla magnetic field in MRI imaging machines. We are going to study MRI machines at the end of this section. So we know that the force acting on a charge is equal to Q times V times B. So force depends on the charge and velocity and the magnetic field. If charged particle moves inside a magnetic field by crossing the magnetic field lines, so there will be a force acting on the charged particle. So how can we find the direction of that force? So we are going to use again right hand rule. So in the right hand rule, 4 fingers will point in the direction of the magnetic field. Thumb will show the direction of the motion of the particle, direction of the vector of velocity, and the palm will point the force acting on positive charge. However, if the charge is not positive, if it is not proton or any positive charge, if it is electron for negative charge, so opposite of your palm will show the force acting on the charged particle. So if I hold my hand like this, so these 4 fingers are showing in the direction of the magnetic field. Thumb must be perpendicular to the magnetic field, here must be 90 degrees, so it will point in the direction of the motion of the charged particle. The palm will show the force acting on the positive charges, but opposite of your palm will show the force acting on negative charge. Right here, if the proton is moving to right in this direction, in a magnetic field in that direction, so force acting on the proton will be out of the page. But if it is not a proton, if it is an electron, if electron is moving to right, so and the magnetic field is up to the plane of the page, in this case force acting on the electron will be into the page. So when we are answering the questions, we are going to draw the coordinate system like this. For example, for directions, this is east, that is west, this is the north, and that is the south. So if the questions directions in the question is given north, east, south, and west, we are going to draw this. But sometimes directions are given as positive phi, negative phi, positive x, and negative x. It can also be given like this, or sometimes it can be given another case. We are going to explain them when we meet such problems. So if a charge is negative, the force directed opposite of the direction of the positive charge. Yani the force acting on the negative charge will be opposite of your palm. The force acting on the positive charge will be in the direction of your palm. The direction of the magnetic force F is always perpendicular to the both velocity and magnetic field. Yes, this force F perpendicular to magnetic field, also perpendicular to the velocity always. Force is perpendicular to magnetic field. Force is magnetic force perpendicular to velocity and direction of the motion of the charged particle. So now let's solve some problems. A sample problem is very easy for that, and I'm not going to explain this one. It's simply they're asking about the velocity, all are given. And this type of problems, generally the directions are a problem to get the directions. For example, let's do the practice problem 2. It says a uniform 1.5 Tesla magnetic field, yani B is 1.5 Tesla, points north. So we are going to draw first direction. So north, south, east and west. These are the directions. So the magnetic field is pointing to north. So I draw the magnetic field lines towards north as you see. If an electron moves vertically downward, so it's the direction of the velocity. So velocity vector must be downward, yani into the page, which is cross, with the speed of 2.5 times 10 to the power 7 meters per second. It is the magnitude of the velocity. What force, magnet direction, will act on it? To calculate the magnet is QVB, you are going to use this equation. Q for the electron is 1.6 times 10 to the power minus 90. It's negative, however, we are going to calculate the magnitude of the force for that, as in we are not going to write negative sign for electron. Always use the positive magnitude of the charge. So Q times V times B, you will get the force as 6 times 10 to the power minus 12. But now the next we should find the direction. So forefinger must point in the direction of the magnetic field. The question says magnetic field towards the north. So then your forefinger will show towards the north. Then thumb must point into the page. It says the particle is moving vertically downward. So then you are going to change direction of your thumb into the page. In this case, this side of your hand will show the force acting on the electron. So then it is in which direction? To the left. But left side here is written as west. So then in this case, this electron on this electron there will be a force acting in the direction of west. So then next one is again an electron. An electron in an electron beam. Electron beam means there are so many electrons, an electron stream. So there is just one electron inside an electron stream, experience a downward force. This time, opposite of your hand, palm will point downward, because question says that force acting the electron is downward. You are going to hold your hand like this. So then, electron beam experiences a downward force, which is 2 times 10 to the power minus 14, while traveling the magnetic field of west. Now, your forefinger must point west. Which side is the west? That side is the west. So then you are going to change your hand towards the west. So, the force is downward, which is opposite of your palm. Thumb must point the direction of the motion of the particle. So, velocity vector is in the direction of the north, because my thumb is pointing in the direction of the north. So calculating the magnitude of the velocity is not so difficult. F magnetic force is QVB. We are going to calculate the B. So to get the V, you are going to divide it by Q and V. QB divided by QB. So simplify them. You can get the velocity by F divided by QB. F is given, Q is given, B is given. Answer, magnitude of the velocity is this. Direction is towards the north. Now, this is the another title. Now, if a particle enters inside a magnet, or it moves inside a magnetic field perpendicularly, This particle, on this particle, for example, this one right here, magnetic field is into the page, given as cross into the page. So then you are going to hold your fingers down like this. So then direction of the particle is motion is the up to the plane of the page. In this case, there will be a force acting on the particle perpendicular to the velocity. If a force is perpendicular to velocity, this kind of force is called centripetal force. Right here, the magnetic force is the centripetal force. This centripetal force causes this object to move on a circle. Yani the charged particle which is moving inside a magnetic field perpendicular to magnetic field lines moves a circular path. However, if the charge is not moving perpendicular to magnetic field lines, now I'm going to show this by two ways like this. Assume these are the magnetic field lines, which is from left to right. If charge enters inside this magnetic field, it can be positive or negative. So with a perpendicular velocity, so like this angle is the 90 degrees, the velocity. So then it will move on a circle. So continuously it will move on a circle. But if charge enters inside this magnetic field with an angle, this angle is theta. As you see, it is not equal to 90 degrees, more than 90. In this case, this velocity will have two components. One component will carry it in the direction of the magnetic field. Other component will cause it to move, make circles inside a magnetic field. Assume that it's a circle, but carried circle. Carried circle makes a helix, or another name, it's called helical path. So if charged particle moves inside a magnetic field perpendicularly, it moves in a circle. If charged particle and moves inside a magnetic field with an angle, so in this case it follows a helical path, and the helix will be in the direction of, will be carried in the direction of the magnetic field of the external magnetic field direction. Now, this is the next title about the magnetic force. Now, until now, we studied the force acting on single particle. It can be an electron, it can be a proton, it can be a positive ion, it could be a negative ion. But now, we are going to talk about the current conductor. First, we should understand what current is. Current is a collection of many particles moving in motion. Now, inside a conductor, there are free electrons. When you apply this conductor with potential difference, these electrons or these charged particles are starting to move, and forming the current. Yani current means the motion of charged particles through a conductor. Now, electric current is earlier discovered than the electron. For that reason, scientists thought that the direction of the electric current is the same of the direction of the positive charge. When we are talking about the direction of the electric current, we are going to think that positive charges are moving in that direction. So when I am defining the direction of the, when I talk about the force acting on a current, I am going to think that charged particles are positive particles. Now, if so many positive particles are moving through the conductor, on each particle there will be a force acting on the particle. But because these particles are inside this conductor, they will transfer this force to the body of this conductor. For that reason, there will be a net resultant force acting on this conductor in the direction of these tiny, small forces. So we are going to use again the right hand rule for finding the force acting on the conductor. This forefinger will show the direction of the magnetic field. Thumb will show this time the direction of the electric current, because charges are moving in the direction of the electric current. The palm will show the force acting on the conductor. Remember, the palm is the force acting on the positive charge, and we assume the electric current as motion of the positive charge. For that reason, we are going to choose this side, and palm, as the direction of the magnetic force acting on the conductor. So if a force is exerted on a single charged particle, yani each charge experiences a force, a current carrying wire also experiences a force due to the sum of, yani addition of the individual forces, these tiny forces, on the charged particles. The force on the particles is transferred or transmitted to the body of the wire through the collision of the with the atoms and making up the wire. So then this force, these tiny forces are, addition of them is transferred to the body of the conductor as the force acting on the conductor. So how can we get the equation for magnetic field acting on the wire? We are going to use the equation for charge BQV. We know that if charge moves with the average velocity v, it will travel the length of the conductor L by a time is t. If you divide distance divided by time, you will get the average speed of the charged particle. So instead of v, I'm going to write L over t. After that, I will get this t to just below the q. Q over t is known as the electric current. Then you are going to get the famous equation, which is F, magnetic force acting on the current carrying what is BIL, or another name is Bill. So now electric current is perpendicular to magnetic field length. If not perpendicular, simply you are going to add here sine theta. Yani theta is the angle in this case, the magnetic field length and the current. But most of the questions are given as perpendicular. So sine 90 is 1. For that reason, you are simply going to use this equation for calculating the magnitude of the magnetic force. I explain how to find the direction of the magnetic force. Forefinger must point the direction of the magnetic field. So thumb must point in the direction of the electric current. Then the palm will point in the direction of the magnetic force acting on the wire. So calculating the magnitude of the magnetic force is not so difficult. For that, as I'm going to pass this practice problem 2, I'm going to solve the questions related to the directions. Now, one question. It is the practice problem 1, page 138. It is about directions. It says 6-meter wire carries a current of 7 ampere towards positive x direction. Now draw the directions: positive x, negative x, positive phi, negative phi. What about z? Z is positive z is like this if given, if needed. That is the negative z. So electric current is in positive x direction. For that, then you are going to draw the electric current in the positive x direction. Its magnitude is 7 ampere. It's moving on a wire whose length is 6 meter. A magnetic force 7 times 10 to the power minus 6 Newton. Your magnetic force is magnitude 7 times 10 to the power minus 6 Newton. Acts on the wire in negative y direction. So then, in negative y direction is the magnetic force. So find the magnitude and direction of the magnetic field producing the force. Calculating the magnetic field is not difficult. Just divide by IL to get the FB alone. IL. So simplify I and L. B is equal to F divided by IL. F is given, I is given, L is given, right? And calculate magnitude. Direction. To find the direction, now you should use right hand rule. The force acting on the wire is negative phi. So then your palm must point in the direction of negative y. So that I'm changing the palm in the direction of negative y. Let me arrange my position. So palm is pointing in the direction of negative phi. But thumb must point in the direction of the electric current. Electric current is the positive x direction. So now I'm changing, if I'm able to do it, my hand to positive x direction. In this case, it is in positive. My forefinger is pointing upward direction. For that reason, magnetic field right here is out of the page in this case. Now let's solve the question about the sample problem. In the sample problem, it says that a wire of 36 meter length of the wire is 36 meter, carries a current of 22 ampere. Electric current is 22 ampere from east to west. So electric current is from east to west. So I am showing the direction of the electric current from east to west. If the magnetic force on the wire is due to the Earth's magnetic field is downward, so F is downward. Downward is into the page, which is cross. So calculate the magnitude of the direction of the magnetic field at this location. Now, Because the force is downward and into the page, your palm must point downward and into the page. And thumb must point in the direction of the electric current. Other forefinger will point in the direction of the magnetic field. So magnetic field direction will be in this case the north, because my forefinger is pointing in the direction of the north. Calculating the magnetic field is not difficult. So F force is equal to BIL. You will get B as F divided by IL. We are going to write the numbers and find the magnitude of the magnetic field. So next title is the magnetic force acting parallel current carrying conductors. Now assume that there are two conductors which carry electric current in the same direction. If they carry current in the same direction, these two conductors will attract each other. But if they carry electric current in opposite directions, they will repel each other. Why is it like this? Because, for example, let's think about this. This is the first conductor. This first conductor produces a magnetic field around everywhere. Also right here. Produce a magnetic field B1. B1 is the magnetic field produced by the first conductor everywhere, but on this location I am choosing. Why? Because I am going to locate the second wire right there. The second carrying conductor experiences a force because of the magnetic field of the first one. And this force is towards the first one. If you use right hand rule, you can understand this. So magnetic field is down into the page right there. Electric current is up to the plane of the page. If you use your right hand trend, you can see that it is towards the first conductor. Second conductor is also producing a magnetic field around. It is out of the page right here. Second conductor's magnetic field is out of the page right here. So first conductor is inside that magnetic field. So for that reason, this first conductor also experiences a magnetic force towards the first one, pardon, second one. So then, in general, I can say that. So first conductor produces a magnetic field on the second one. Because of this external magnetic field, second one experiences a force. Second one produces a magnetic field on the first one. Because of that external magnetic field of the second one, first one experiences force. So these two forces are in these two conductors attract each other if the electric currents are in the same direction. So sticks, but if they are in opposite directions, they will repel each other. And next title is loudspeaker. So loudspeaker uses magnetic force because in loudspeaker there are three components. One of them is the external magnet. When you see you see that the magnet at the body of the loudspeaker. Inside this magnet there is a coil. This coil will carry the current, and this coil is connected to a paper cone. So when you give electric current to this coil by talking a microphone, you send electric signal. This coil is starting to move because of the magnetic field of the permanent magnet back and forth. This motion back and forth also moves or vibrates the cone. Vibration of the cone produces the sound. This is how a loudspeaker basically works. So there's a magnet. Inside this magnet there's a coil. Coil is connected to a cone. When you give electric current to the magnet, when you buy, for example, talking a microphone, you can produce an electric current. You can send this electric current to this coil. This coil is starting to move according to the frequency of your sound and also the intensity of your sound. So then it's starting to move the cone of the loudspeaker, and this cone produces rarefaction and compression regions and producing the sound. Second important device is galvanometer. Galvanometers are coils normally. This galvanometer is used for construction of both ammeter and voltmeter. Now there are 1, 2, and 3, 4 as important elements for the galvanometer. One of them is we need a permanent magnet. From N to S, magnetic field is formed. A coil is located inside this magnetic field. This coil carries a current in one side if it is into the page, in the other side it's out of the page. If I draw it, it's like this. From the rear view. If you look from the above, you are going to see it is like coil like this. So if the current is entering from one side, So leaving from the other side. If it's into, right there it's out. Into, it is out. So for that reason, these currents are in opposite directions but inside the same magnetic field. For that reason, force acting on them is opposite. If right here force is down to the plane of the page, here is up to the plane of the page. These forces produce a torque right there, and this torque, clockwise torque, produces the rotation. This coil is connected to the needle of the galvanometer. Needle is starting to rotate. This angle of the rotation, theta, is directly proportional to the electric current. If you give more electric current, it rotates more. So according to the angle of rotation, you can understand how much electric current is given to this device. So galvanometer can be, as I said, galvanometer is simply a coil. If it is coil, we say it's galvanometer. Of course, every conductor, if it is a coil, has a resistance. Galvanometer also has a resistance. However, its resistance is very small. For that reason, if its resistance is very small, if you give a huge current to this galvanometer, so this coil will burn. For that reason, when we want to use this galvanometer to measure electric current, we should get the 90% of the color through this resistor, which is called shunt, connected in parallel. So to stop the burning of the coil, we are going to connect a resistor in parallel with the galvanometer. Remember, I said galvanometer is just a coil. Coil also had as a resistance, I'm going to say this is Rg, but very small resistance. If you directly give all the current to this coil, it will burn. To stop burning, you are going to connect a resistor in parallel. This resistor will get the almost 90% of the current. The 10% of the current will pass through the galvanometer. For that, you are going to stop burning of the coil. So a galvanometer is converted into ammeter if a low value resistor, which is called shunt, is connected in parallel with the galvanometer. So in parallel combination, electric current, main electric current is equal to sum of the electric current in the branch. Yani I is equal to Ig on the galvanometer plus Is, which is electric current on the shunt. Second important parallel combination is potential differences on the galvanometer. Yani on the coil will be called potential difference on the shunt. So potential difference on the galvanometer is this electric current times resistance. Remember, V is equal to I times R, which is one of the most important equation in physics. V is equal to potential difference current times resistance. Current on the galvanometer times resistance on the galvanometer is the potential difference on the galvanometer must be equal. Current on the shunt multiplied by resistance on the shunt, which is the potential difference on the shunt. So by using these two equations, I'm going to answer the questions. Now let's do one other question. It says, we want to use a galvanometer of internal resistance 5 ohm in order to measure electric current of intensity up to 10. So this is the resistance of the galvanometer coil. It is 5 ohm. We are going to measure a current 10 ampere, but this current is so big. If you use this current directly, you are going to burn that. For that reason, you are going to pass maximum 1 ampere current through this galvanometer. If this is 1 ampere, 10 is coming, 1 is going from the galvanometer, so 9 ampere must pass through the shunt, because 9 plus 1 must be equal to 10. After that, you are going to get these numbers and write it here. Galvanometer, 1 ampere current is passing to the galvanometer. Resistance of the galvanometer is given as 5 ohm, is equal to electric on the shunt must be 9 volt, so it's 9 ampere, pardon, times resistance of the shunt. So after that, you are going to get the resistance of the shunt by 5 divided by 9, which is equal to 0.55 ohm. So as you see, it is a very low resistor. Even galvanometer is lower than galvanometer. So then, how much of this passing through this? 90% of the current passing through this through the galvanometer. So less number of the amount of current is passing. So another one is to use the galvanometer. And voltmeter. But to do that, we are going to connect a resistor in series. But this resistor will have a great value. So then, electric current passing through the circuit will be smaller if the resistance is big. So in series combination, because the high value resistor is connected in series with the galvanometer, so then electric current will drop, but the same electric current will pass through the galvanometer and resistor. But right here, potential difference are different. So potential difference on the galvanometer plus potential difference on the resistor, addition of them will be equal to total potential difference of the circuit. So then, by using these two equations, I'm going to answer the question related to galvanometer used as a voltmeter. Now let's do first them. A moving coil voltmeter measures potential difference between 0 and 5. A moving coil means this is the only galvanometer itself. It can measure only 5 volt. Question says that. So a galvanometer measures maximum 5 volt. It's more than 5, it can burn. So then, if the resistance of the voltmeter is 500 ohm, yani resistance of this galvanometer is 500 ohm, what is the intensity of the current through the galvanometer if it is 5 ohm? So you are going to use the Ohm's law. Electric current is equal to potential difference divided by resistance. Potential difference of the galvanometer is 5. Resistance of the galvanometer is 500. So maximum current which can pass through the galvanometer is maximum current which coil tolerates is 0.01 ampere. Now we are going to use this galvanometer to measure a potential difference greater than 5. What is the resistance? In this case, we should connect a resistor. What is the resistance of the resistor that should be connected in series with the voltmeter in order to measure the total potential difference of 30 volt? Now, total potential difference here will be 30 volt. But we know that 5 volt of this one is on the galvanometer. The rest must be on the resistor. What is the rest? 25. Because 25 plus 5 is equal to 30. We know that maximum current which can pass through the galvanometer is 0.01 ampere. If 0.01 ampere is passing through the galvanometer, the same current must pass through the resistor too. So I know what potential difference on the resistor is. I know what the electric current on the resistor is. So from the Ohm's law, I can calculate the resistance by V divided by I. So V is given as 25. I is as 0.01. When we divide, you are going to get the answer as 2500 ohm. So this is the resistance of the resistor which is connected in series with the galvanometer. So, and one more last question, the hardest question I am going to solve. Question number 2 and 5 I will answer, the rest are easy. Question number 2, there is an electron moving north. So direction of the electron is north. Encounters a uniform magnetic field. If the magnetic field points east, so direction of the magnetic field is east. So what force is acting? What is the direction of the magnetic force acting on it? Simply you are going to use right hand rule. So forefinger must point to west. It is east. The particle is moving to the north. So then the magnetic force acting on the electron will be opposite of your palm. Yani it is out of the page or outward. And last question is the question number 5. Find the direction of the magnetic force on the current carrying wire in the figure. In the current carrying wire, as you see, the wire is located between the N and S pole. So electric magnetic field is flowing from N to S. Always remember this. So magnetic field direction will be in that direction. So I'm going to hold my hand in the direction of the magnetic field. So thumb must point in the direction of the electric current. So then palm will point the force acting on the conductor. It is also out of page or upward.